I'm Mark Rennies, and this is Euler's Melting Pot. In this challenge, we try to complete every Project Euler problem in a different programming language. Today's challenge is problem number 12. Find the first triangular number to have over 500 distinct divisors. The nth triangular number is defined to be the sum of all natural numbers from 1 up to and including n. The first triangular number is 1. The second is 1 plus 2, or 3. The third is 1 plus 2 plus 3, or 6, and so on. The next few triangular numbers are 10, 15, 21, and 28. We want to identify the first triangular number which is divisible by more than 500 different positive integers. These numbers are called triangular because if you draw the summation with each addend in a separate column, the resulting diagram resembles a triangle. First, let's talk about Pascal's triangle. Pascal's triangle, named after Blaise Pascal, is a mathematical array that we can draw to represent certain functions that appear commonly in probability and combinatorics. To construct Pascal's triangle, we begin with a small two-row triangle consisting of only ones. To add another row to the triangle, we first place a 1 on each side of the triangle. Then, for the interior, we sum the two numbers immediately above and write that number at the new position. In the third row, the numbers above our interior are 1 and 1, so 1 plus 1 equals 2. The fourth row consists of 4 numbers. The outer two, as always, are 1s. The left interior position is below a 1 and a 2, so we write 1 plus 2 equals 3. The right interior position is below a 2 and a 1, so we write 2 plus 1 equals 3. We can produce the fifth row similarly, getting 1, 4, 6, 4, 1, and so on. Pascal's triangle has no bottom, so it can be extended indefinitely. We can use Pascal's triangle to calculate the binomial coefficient. The binomial coefficient, which is written as n choose k, takes two input arguments n and k and returns the number of ways to select k balls from a bucket of n distinct balls. This sort of problem appears frequently in combinatorics and probability theory in some form or another, and the binomial coefficient can be read off of Pascal's triangle easily. N choose k is merely the position in Pascal's triangle at the nth row and kth column, with both values 0 based. For example, suppose we have a bucket containing 4 balls of different colors. Let's say red, green, yellow, and blue. And suppose we draw 2 balls from that bucket at random. Pascal's triangle can tell us the total number of distinct ways we can do this. 4 choose 2 indicates that we should look at row 4 and column 2 of our triangle. Counting from 0, row 4 is the row consisting of 1, 4, 6, 4, 1. And column 3, again, counting from 0, is 6. Let's enumerate all of the possible ways we could draw 2 balls from this bucket just to check our work. The 4 balls in the bucket are red, green, yellow, and blue. We could draw the red one and the green one. We could draw the red and yellow balls together, or we could draw the red and blue ones. If we don't end up drawing red, we could draw green and yellow, or green and blue. Finally, we could end up getting yellow and blue. That's a total of 6 possibilities. We can also calculate the binomial coefficient directly using factorials. N choose k is equal to n factorial divided by the product of k factorial and n minus k factorial. Again, we can check our 4 choose 2 work against that formula. 4 factorial is 24, 2 factorial is 2, and 4 minus 2 factorial is also 2. So 4 choose 2 is 24 divided by the quantity 2 times 2, or 6. You may wonder why we're taking a trip into combinatorics to solve this problem. Remember that the first few triangular numbers are 1, 3, 6, 10, and 15. Notice that the triangular numbers appear along a diagonal in Pascal's triangle. If we start at the far right of the third row and then follow the triangle down and to the left, we encounter all of the triangular numbers in a sequence. This means that the nth triangular number appears in Pascal's triangle in row n plus 1 and column 2, counting from 0. That is, the nth triangular number can be written as n plus 1 choose 2. And that gives us a formula in terms of factorials. Namely, the nth triangular number is equal to n plus 1 factorial divided by the product of 2 factorial and n minus 1 factorial. We can take this one step further. Remember, the k factorial is the product of all integers from 1 up to and including k. Let's write out the products explicitly. The numerator consists of n plus 1 times n minus 1 times n minus 2, all the way down to 1. In the denominator, 2 factorial is simply 2. Then the other term, n minus 1 factorial, is n minus 1 times n minus 2 times n minus 3, again, all the way down to 1. Crucially, the numerator and denominator contain the exact same terms from 1 up to n minus 1. The numerator simply has a few extra terms on top of that. We can cancel off all of the common terms, and our triangular number formula simplifies to n times n plus 1 divided by 2. Great, let's write some code. We'll start in C++ this week. We need 2 functions. One to count the number of divisors, or factors of a number, and the other to calculate the nth triangular number given n. First, our factor count function. This is straightforward, and we've done variants of it several times already. We keep a total count and iterate from 1 up to and including n. For each value, we check if it divides evenly into n using the modulo operator, and if so, we increment our count. Finally, return the total count. Note that we iterate from 1 up to and including n, since n is a completely valid factor of itself. Now we need a function to calculate the nth triangular number. We have a very easy formula for doing so this function is very simple as well. Finally, our main loop. We keep an index which starts at 1 and tracks which triangular number we're looking at right now. Then we calculate the triangular number, count its factors, and see if the count is greater than 500. If so, we print it out and terminate our program. This return statement is the only way to exit our for loop since we haven't supplied an exit condition in the loop header itself. This program isn't fast enough. It's probably correct, but it's far too slow for me to wait around and find out for sure. Fortunately, we can optimize our factor counting function quite a bit. As we've discussed before, factors of a number always come in pairs. For instance, the factors of 24 are 1, 2, 3, 4, 6, 8, 12, and 24. These can be paired off as follows. 1 times 24, 2 times 12, 3 times 8, and 4 times 6, each of which multiplies to 24. Further, in each pair, one of the factors is less than or equal to the square root of n, while the other is greater than or equal to the same. So instead of iterating from 1 up to n, we can iterate from 1 up to the square root of n, and every time we find a factor, we increment our count by 2 to account for the paired term. The only other quarter case is one where the square root of n is an integer. In that case, when we encounter a factor exactly equal to the square root of n, we only want to count it once, since n is equal to the product of this factor with itself, not of two distinct factors. Now let's update our function. We iterate from 1 up to the square root of n, then inside our loop, when we find a factor, we check if the factor is exactly equal to the square root of n. If so, we add 1 to our total. If not, then the factor must have a paired term strictly greater than the square root of n, so we add 2, 1 for the factor we just found, and 1 for its paired term. This program runs, and it produces a result nearly instantaneously, but there's actually even more work we can do. To optimize this program even further, we need to talk about coprimality. We've discussed prime numbers several times in this series. A prime number is a number whose only divisors are 1 and itself. Worded slightly differently, a number is prime if its only proper divisor is 1. Two numbers are coprime or relatively prime to one another if the only factor they have in common is 1. For instance, 4 and 6 are not coprime since 2 divides both of them evenly. 10 and 33, on the other hand, are coprime. The factors of 10 are 1, 2, 5, and 10, while the factors of 33 are 1, 3, 11, and 33. The only factor they have in common is 1. Now, interestingly, two adjacent numbers are always coprime. That is, 1 and 2 are coprime, 2 and 3 are coprime, 3 and 4 are coprime, and so on. To see why this is, consider two numbers whose difference is 1. Call the smaller number n. Then suppose n has a non-trivial factor k. That is, n mod k is 0. Then if we add 1 to both sides, we find that n plus 1 mod k is 1. Hence, k is not a factor of n plus 1. We can do the same thing in reverse. If some number k greater than 1 divides n plus 1, then n plus 1 mod k is 0. So n mod k must be k minus 1, and thus k does not divide evenly into n. So n and n plus 1 cannot have any non-trivial factors in common. With all of this in mind, let's take another look at our formula for the nth triangular number. The nth triangular number can be written as n times n plus 1 over 2. 1 of n or n plus 1 must be an even number. So if we reorganize this, we can write the nth triangular number as either n over 2 times n plus 1, or n times n plus 1 over 2. In either case, we've written the nth triangular number as a product of two integers. Further, n and n plus 1 are coprime for the reasons we just discussed. And if we take an integer and divide out one of its factors, then the quotient clearly has fewer factors than the original number. So since n and n plus 1 are coprime, n over 2 and n plus 1 must be coprime as well, and the same for n and n plus 1 over 2. That is, we've written the nth triangular number as a product of two coprime integers. There's one other useful property of coprime integers I haven't mentioned yet, and it has to do with the distinct factors of coprime numbers. Clearly, if we have a factor a of n and a factor b of k, then a times b is a factor of n times k. But if the two numbers n and k happen to be coprime, this fact also works in reverse. When n and k are coprime, every factor of n times k can be written uniquely in the form a times b, where a divides n and b divides k. Let's take a moment to see why this is. Take some pair of coprime integers and consider their product. Suppose we have some factor of the product. Recall that every positive integer can be written uniquely as a product of prime numbers, so write the factor as a product of primes. Now, our two multiplicands are coprime, so each of these prime factors can only divide into one of the two multiplicands. If we take the primes and group them so that each prime sits with the multiplicand it divides, then we can multiply each group together. Once we've done this, we have a number that divides our first multiplicand and a number which divides our second, and their product is the original factor. Further, this separation is unique, since the coprimality property guarantees that none of the primes can move to the other multiplicand. All of this is to say that if we have two coprime integers n and k, we can count the total number of unique factors of their product n times k by counting the factors of n and counting the factors of k independently, and then multiplying the results together. Let's rewrite our main loop to take advantage of this new fact. Inside our loop, we separate our n and n plus 1 terms and divide the even term by 2. Now we have two terms which are coprime and which multiply to be the triangular number we're interested in. We count the factors of the left and right terms separately, then we multiply the counts and see if the product is greater than 500. If so, we print out the product of our two terms and exit. This program runs instantaneously, and we're ready to translate it into the language of the week. The language this week is 05AB1E. According to the ESOLangs article, the language's name can be pronounced more or less however you like. For this video, we'll call it Osable. Osable is a stack-based golfing language in the same vein as GolfScript and CJam. Osable is actually quite straightforward as a language. Its primary selling point is its sizable collection of primitives. The language has over 200 distinct 1- or 2-character commands, which perform various arithmetic and control flow operations. Many of these commands are overloaded based on the types of their inputs, for a total of over 400 unique functions that can be accessed by these commands. There's no more trickery to this language. Unlike GolfScript and CJam, Osable doesn't have a function type. All of our code runs at the top level and operates on 3 simple data types: numbers, strings, and lists. And all of the built-in functions happily convert between these types whenever it makes sense to do so. We're going to jump right in and write some Osable code. The algorithm we'll write is very similar to the C++ code we just finished. We'll iterate starting at 1. At each iteration, we'll calculate the two coprime integers, which multiply to equal our current triangular number. Then we count the factors of each, multiply the counts, and check if we've exceeded 500. If so, we'll break out of the loop, calculate the triangular number in question, print it, and terminate. If not, we'll increment our current iteration index and continue. First, we push our starting index onto the stack. As in many stack-based languages, integers written literally into the source code simply push themselves onto the stack when executed. Next, we begin our main loop. In Osable, the simplest loop, and the only one we'll need in this case, is an infinite loop, delimited by a pair of square brackets. The loop will run forever unless we break out of it with the hash instruction later. Inside our loop, the top of our stack is I, the current loop iteration index. We're going to do some stack manipulation, so we want to store a copy of the current loop index somewhere else in memory. Osable offers two general-purpose integer variables that we can use for whatever we need, x and y. To write to these variables, we use the commands u and v respectively. In our case, we'll only need one, so we'll use x. Duplicate the top of the stack and then pop the top and store it in x. We'll need this value in a moment. Next, we increment the value on the stack with greater than. The top of the stack now stores our loop index plus 1. Next, we want to check if our n plus 1 term is even. If so, we need to divide it by 2. If it's odd, we don't want to do anything with it yet. We duplicate the top of the stack, then check if it's even. Checking if a number is even is actually built into Osable and is written using e with grave. Now we want to do something if the top of the stack is true. Osable offers a sort of rudimentary if statement which begins with a lowercase I and ends with a closing curly brace. Inside our if statement, we push 2 and then divide the top two stack elements. Now we have our first multiplicand. Let's count its factors. By this point, it shouldn't come as a surprise that produce a list of all factors of this number is a built-in function in Osable. The function's name is n with tilde. Once we have the list, we'll take its length with lowercase g. We have our first factor count. Now we need to do the same thing with I. First, we push the value of the variable x, which stores our original loop variable I. Then we check if it's even, and if so, we divide by 2. Finally, we count the factors of either I or I over 2, depending on which case we're in. Now we have our two factor counts. Multiply them together, then check if the total is greater than 500. Since the typical greater than character is used for incrementing numbers in Osable, an actual greater than comparison is done with this Unicode, rightward pointing, angled quotation mark. Now the top of our stack is a true value if we found our solution. If not, the top of the stack is false. If the top of the stack is true, we break out of our loop with the hash command. Note that we don't need to wrap the hash command in an if statement like we did our division operation. Hash pops a value off the stack and breaks the loop if the value is true, effectively acting as a comparison and a conditional jump all in one. Finally, if we're still in the loop, the stack is empty, but at the start of the loop, the stack contained one value, which was the loop index. We push x, which contains our loop index, back onto the stack and increment it by 1. Finally, we terminate our loop with a closing brace. If we broke out of the loop, we did so when the stack was empty, so at this point in the code, the stack contains no values. The value currently in the x variable is the loop index at which the correct triangular number was found. So we want the xth triangular number. Push x twice. increment the second x, then multiply the two together. Finally, divide by 2. The semicolon is simply a shortcut for division by 2. Once we have our triangular number, we print the result with the equal sign and terminate the program. And that solves Project Euler problem number 12 in OSIML. Tune in next time when we solve problem number 13 in SED, the stream editor.